This one is good.
What's over?
Yeah.
On the head.
Right. Okay. So after a small technical hiccup, so it's my pleasure to introduce as well local Francesco Orabona, who is going to be speaking about portfolio selection and confidence intervals. Yeah. Are you comfortable with the interruptions for questions, or do you prefer the end?
I don't know. I'm comfortable. Yeah. Please
do
stop me at any moment. Okay. So good morning, everybody. This talk will be about stochastic, but from a kind of a different point of view. So we'll start from a problem that is actually non-stochastic. It's completely adversarial. And then I'll show you how to use it to obtain a result in the stochastic world. So this will be a brief outline of my talk. I will talk about what is online learning, and then a particular problem in online learning that is portfolio selection. And finally, I'll show you how to go from portfolio selection to concentration inequalities. So let's start with the first part, online learning. So what is online learning? Online learning is a framework it's still a machine learning framework, but it's slightly different from the usual one in the sense that it's like a game that goes on in rounds. And on each round, you have an agent that is receiving some input, let's say, for example, an image. And after each input, it has to predict something related to the task that it's solving. For example, let's say that this is a robot, it's navigating an environment, it receives an image, and after each image, it has to say which room it is in. So it will output its prediction. Now, just after each prediction, this is essentially in the online learning framework, you receive feedback from the environment. So the environment will tell you if you're correct or not, okay? However, there is an essential ingredient in this entire framework. We don't assume anything about the environment. We don't assume that the environment is, for example, that the samples are IAD from a distribution. In fact, we don't assume that there is a distribution. We don't even assume that the environment is correct. It's actually the opposite. The environment is an adversary that is trying to push as many mistakes as possible inside the learner. Okay, so a little bit more formally, we have a number of rounds, we observe some data, we predict something in some feasible space, in some feasible set, and then we suffer a loss that basically measure how wrong is our prediction. And now everything is generated by an adversary. The X are generated by, the Z are generated by an adversary. The loss itself that can change in each round, it's not the same loss in each round, it's also selected by an adversary. And you can see that there is no real separation between training and testing that is classical machine learning. Machine learning, you would train on something, then stop, and then say, okay, this is good, let me use it. This instead, it's a framework in which you learn forever, in a certain sense, and you are not interested in a performance outside of what you're doing. You are interested in the performance right now, during the game. And if you want, this is the closest thing to reinforcement learning where you can still prove easy theorems. The difference with reinforcement learning is that there is no state. And so the environment is static in a certain sense. And you receive feedback just after each action.
So just a question.
Yes.
To put it in context, do you think that there's a connection with filtering problems actually and data simulation where you actually get a stream of data and you're trying to update your...
Yeah, there is, yes, indeed there is.
To Bayesian filters, for example?
Yes. I'm not super familiar with that setting, but I'm sure there is.
Yeah, it looks like.
Okay, so what can we show in this setting? Given that everything is adversarial, you cannot really say, I want the cumulative loss of the algorithm to be small, because this can be as high as possible, because again, everything is generated adversarially, so this can be arbitrarily high. But so it makes sense, instead of to say that the cumulative loss of the algorithm should be small, it makes sense to say, I want the cumulative loss of the algorithm to be minus the cumulative loss of the best fixed prediction in the same feasible set where you are outputting your prediction to be small. Okay, so why this makes sense? Because again, the losses can be arbitrarily difficult. And so your job can be arbitrarily difficult, but it's fine as far as you compare yourself with respect to the best fixed prediction. Okay, and so if everything is difficult, there is nothing to learn, but that's okay. You are still as good as the best fixed prediction in that set. If things are easy, of course, again, you want to be as good as the best in the set. Now, we will say in online learning, we will say that an algorithm is good, that algorithm has no regret. And by the way, we call this difference regret, when this difference is sublinear over time. Okay, and why we care about this? Because basically means that on average, the regret is going to 0. So this means that on average, your cumulative loss is approaching the cumulative loss of the best in the set. Okay, and why this is good? Because the best in the set, this, you see, this mean is selected at the end of the game. At the end of the game, you realize what was the best choice. And so this means that the mean basically knows the future. The argmean knows the future. And so you're trying to compete with something that knows the future. This is your job.
Sorry.
Now, yes.
So in the setup that you had before, you had the x as a function of an input, which
Right. There might be some additional data. Sometimes it's there, sometimes it's not. But for generally you can have it. For the rest of the talk, I will not assume that you have any additional input. Okay.
Okay. So
you don't have anything. In each time step, you just have to output this vector in your feasible set, and after your prediction, you receive the loss.
Right. So, but it means that your inputs, so your best is literally the best because your input is not changing.
Yes.
Okay.
Yes.
Okay.
And so again, there is no stochasticity. Everything is non-stochastic, and so all the data here in this setting is the additional inputs that, again, in this particular case we don't have, and the LT. Everything is controlled by an adversary. And by the way, the adversary is adaptive. So the adversary knows what you did in the rounds before, and he can adapt to it. He knows the code of your algorithm, he knows everything. Okay, so why we should study this setting? It seems very hard to prove anything, and it seems very far from reality. But actually, this is very close to reality. So there are a lot of problems that are intrinsically online. So the classic problem that we give as examples in all our talks is spam filtering. If you think about spam filtering, what is the job of the algorithm? Basically, it has to classify mails if there are spam or ham. And what is the feedback that you receive? The feedback is every time a mail was classified wrongly, you go back to your spam folder, you look at the mail and say, oh, wait, this was an important mail. You put it back in the inbox. This is exactly the feedback that you are giving to the algorithm. Now, if you think about what is here, the adversary, who is generating all this data, the adversary are the people that are generating the spam mails. They're not IID. For sure, they are not from a fixed distribution. It's the opposite. They're trying to fool you. They're trying to craft mails that they look like ham, but in reality, they are spam. Okay, so this is the classic online learning problem. But there are also other problems, and in particular, later I will show you this stock market prediction that are, if you don't want to assume anything about the stock market, they can be modeled in this way. They can be modeled as an online learning problem in which anything can happen in each step, and you just want to be as good as the fixed strategy. There are also, online learning, it's famous because there are a bunch of problems that are related to advertising. So, for example, when you go on websites and you browse a website and you see all these banners that are appearing on the website, that is an online learning problem. How do the website knows what to show you? For sure, the users that are visiting the website, they're not coming IID from a distribution. There is nothing stochastic about it. It can be anything. And basically, in each time step, the algorithm will choose an action that is basically one of the banners that it can show you. And you are giving feedback to the system. What is your feedback? You click on the banner or you don't click on the banner. If you click on the banner, you like it. So the prediction of the algorithm was good. If you don't click, you're saying, I don't like it. Okay. And this is a particularly hard online learning problem that we call with banded feedback. And the reason is that every time you say that you don't like the banner, so you don't click on it, you don't say what you would have liked instead of that. So you are just saying yes or no and nothing else. Okay. And again, there are a lot of papers on this, and again, this can be solved in the sense that we can show algorithms that have sublinear regret. Okay, so given this introduction of online learning, let me show you an actual example of an online learning problem with an algorithm to solve it. And the example is portfolio selection. So what is portfolio selection? I know that there are people that will talk about portfolio in the next days, so I don't want to claim here that I will show any algorithm that will actually make you rich, okay? This is mostly a theoretical thing in a certain sense. Anyway, so there are these stocks, and you want to invest money on them. And let's say that you start just with $1, and on each day, what you do is that you buy stocks at the opening prices, and then at the closing time, you sell all of them. Okay, and you keep doing this every day. And so your job each day is just to decide how you want to distribute your money on top of these stocks. That's it. Now, let me denote by WTI the ratio between the closing and opening price of stock I at day T. Okay, so if this number is bigger than one, you're making money. If it is smaller than one, you're losing money. If it is 0, the stock crashed completely. You lost all your money. Now, what is a very natural strategy? First of all, there is a very natural strategy that most of people use in US, and I also used in the US when I was living in US. That is buy and hold. That basically say you decide that you like certain stocks, you buy them, and you never sell them for the rest of your life until you retire. This is a classic approach, but it's very easy to show that it will not give you any money if the stocks are not increasing. The stocks have to increase in order to gain you money. And instead, there is another strategy that is better, that will gain you money even in the case in which nothing is going up. If stocks are just oscillating over time, there is a better strategy that will extract money from the market. And this other strategy is called a constantly rebalanced portfolio. What is this idea? This idea is that you just use a fixed distribution over your stock, over the entire capital T rounds. Okay, so each day you wake up and you decide that distribution over your stocks is, for example, 50% of your money on Google, 20% on Microsoft, and the rest, I don't know, let's say Meta. Okay, and that's it. This is your distribution of money. So you buy the stocks according to this distribution. Then at the end of the day, you sell all of them. And the next day, your money will be changed, but again, you use the same distribution. So you buy the stocks in the same ratio each day. Okay. So why this works? Let me show an example. It might not be immediately intuitive why this algorithm will extract money from a market that just goes up and down. Let's say that you just have 2 stocks, and the market gains, the W, in each day are just 1, 1/2, 1, 2, 1, 1/2, 1, 2. Okay, so the first stock basically is giving a market gain of 1. So this means that in each single day, the stock is not doing anything. This is basically equivalent to taking your money and putting it into the drawer and nothing else. At the beginning of the day and at the end of the day, the value of the money will be the same. Okay. The other stock, instead, the only thing that is doing is that one day is halving its price and the next day is doubling it. And it's keeping doing this forever. Okay. Now it's very clear that if you just buy and hold in any proportion you like these 2 stocks, you will never make any money out of this. Okay. Instead, the constant rebalanced portfolio, in which you just allocate your money as 1/2 of the first one and 1/2 of the second one, will give you that the rate at which your money will increase is 1.06 to the T, where T is the number of days. Okay, and there is nothing magic about it. You just have to literally do the calculation and you will get this now. Okay, so you can see from this example that the market is basically not going up, but instead your money are increasing exponentially over time. And this is, by the way, this is a huge, I mean, it's never so good, because this is actually says that in 12 days, your money will double and will keep double every 12 days. Okay, so this is just today that the constant rebalanced portfolio is a very, very simple strategy, but it works. It does something. Okay, might not be, again, I'm not claiming that if this is the best in the stock market world, but this is decent enough. Okay, so now what is our job? We want to transform, we want to write an online learning problem on top of this problem. And the constant rebalance portfolio will be the best strategy with which we compare. We want to be as good as the best constant rebalance portfolio. Okay, so let me write some formulas. So what is the wealth of the best constant rebalance portfolio at time t? This is the sum over the stocks of how much money you put on the stocks multiplied by the market gain. Okay, this tells you at the end of the day if you got money or you lost money, and you just sum over your stocks. And how much money you put in each day, it's how much money you have at the beginning of the day multiplied by the ratio. Okay, this is the ratio that you decide. Remember, constant rebalance portfolio is a constant distribution of your stocks. So this is UI, this is constant over time. Okay. So this means that if you keep doing this after capital T days, you get that you can just unroll this relationship and you get that if you start with $1, this is the money that you will get at the end of the game. Okay? That depends on this vector U, that is your distribution over the stocks. Now, what is instead the algorithm? And in one important thing, what is the best distribution? This is known only in retrospect, right? Only at the end of the game, you can look at the stock market over these capital T days and you can say, oh, this is what I should have done, right? And how do you do that? Well, it's simple. You just take this function here and you maximize with respect to U in the simplex. That's it. This is a convex problem. So you can easily do that. Okay, so what is instead what is the algorithm will do? We want an algorithm to do exactly the same strategy, to approximate this strategy. So the algorithm will do exactly the same thing, but the difference is that the algorithm will decide the distribution X in each round, based on the past. Based on what happened in the past, the algorithm each day will tell you, this is the distribution that I think you should use. And so the wealth of the algorithm is exactly the same, but the only difference is that now XT is changing in each round. And instead, the best constant rebalance portfolio uses a fixed vector in each round. Okay? That's it. So this is the wealth of the best. This is the wealth of your algorithm. Now, so to summarize, let me show you again these two formulas. Now, you would like to write an online learning problem, so you would like to write the difference between two objects, the loss of the algorithm, the loss of the best. But these are quantities that they can grow exponentially, as I showed you before in the example. And it doesn't make any sense to take differences between quantities that are exponential. And so instead, it makes more sense to take ratio between them. Or in a very equivalent way, you can take the difference of the logarithm. Okay, and this is what we will do. We will define the regret as the difference between the log wealth of the algorithm and the log wealth of the constant rebalance portfolio. Okay, actually in reverse, because this is bigger. Okay, so this is the log wealth of the algorithm. It's just the logarithm of this quantity, and this is the log wealth. This is the log wealth of the best, and this is the log wealth of the algorithm. Now, if you look at it now, it's clear that this is exactly the same shape of the problem that I showed you before. And what are the losses that you receive in each round? These are your losses. Minus log WT transposed X. And this is a function of X. Okay, and this is a convex function, by the way. So we transformed our problem of portfolio selection into an online learning problem in which all the losses that you receive are convex. There is nothing stochastic. They are chosen by the market that we assume to be adversarial in the sense that it can be anything. Okay. Any question till now? Is it clear, the setup? Okay, sounds good. Okay, so what do we know about this problem? It turns out that this is a classic problem. Thomas Cover, the guy from information theory, designed an algorithm to solve optimally this problem. And in particular, design an algorithm that has this kind of regret. The regret will be d minus 1 divided by 2. Remember, d is the number of stocks, and is logarithmic in time. Okay? And he also showed that everything is optimal in this regret. The only thing that is slightly suboptimal is the constant 2 inside the log, but that's it. The rest, everything is suboptimal. The main, even the leading constant here is it's optimal. So what does it mean? What does it mean if we translate this regret into money? Remember that this is the regret. The regret is defined as a difference between log wealth. Okay, so the log wealth of the best minus the log wealth of the algorithm is at most a logarithmic quantity in time. This means that if I exponentiate everything, the best wealth will be some exponential quantity in time. Okay, as I showed you before, that is the best wealth. How much is the wealth of the algorithm? Is a polynomial factor away from this. Okay, why a polynomial? Because you take the exponential of this thing, and the order of the polynomial will be exactly this factor here. Okay, and this is good because again, you're competing with somebody that is making an exponential amount of money, and you're just a polynomial factor away. So, you know, it's a very small thing with respect to gaining a lot of money. So what's the basic idea of how the algorithm of cover works? And by the way, he called this thing universal portfolio. Universal in the sense that the regret is always sublinear with any sequence of stock markets. So the basic idea is the following. It's more from statistics, if you want. Do you predict in each round according to an average? And what is this average? What is the probability that you use in the average? The probability contains two factors. One is a prior. This is a prior that you have on top of all the possible allocation of money on top of these stocks. And there is a way to choose the prior that is not super important at the moment. And what is this other term? Instead is the wealth that the portfolio X made over the past. Okay, so you look at these two things. There is a prior that you have on what you should do over these stocks, and then you look at each single portfolio, how good was over the past. You construct a probability distribution with these two ingredients, and you take the average of the portfolio allocation according to this probability distribution. Okay, this is the strategy. And what is the prior? He also showed that the optimal prior is a Dirichlet 1/2, 1/2, 1/2, 1 on each stocks distribution. This is the optimal thing. Now, the integral is a little bit annoying, but it can also be approximated in polynomial time. There are later papers in which they showed how to do it. Now, why this thing works? This thing works because it's possible to show, and this is very easy, that the wealth of the algorithm, every time you use such strategy, is equal to this expression. What is this expression? This is the expectation of the constant rebalance portfolio weighted according to your prior. Okay? Nothing else. And so why this works? You basically want to compete with respect to the best constant rebalance portfolio. Okay, so there is an optimal allocation of money somewhere that you don't know, and you will know only at the end of the game. Your prior, if your prior puts enough mass, enough probability mass around that point, then you're fine, because this average, the log of this average, will be close to the log of the max of this expression. This is what he proved. Okay. Okay, so these are all known results. Let me show you also something that, you know, how all these things actually works in practice. I implemented these things. So I took the stock market of two stocks. This is the market gains as I define you. So it's closing price divided by opening price of Microsoft and Tesla. And the green line is the universal portfolio. And the red line is the constant rebalance portfolio. So the constant rebalance portfolio, the red line, is calculated such that at the end of the entire game, your wealth is maximum. Okay, so it's calculated exactly just according to have this point as high as possible. And the green line is the performance of the universal portfolio that you can see it's always very close to the best thing that you should have done. Okay. Again, let me remind you, the constant rebalance portfolio is calculated only at the end of the game, so you cannot really use it. Instead, universal portfolio in every day just decides based on the past, so it's an actual strategy that you can use. Okay. Now, why compare to the best rebalance portfolio? One might say, okay, this is a very weak strategy. We have much better strategies, and I agree. But first of all, without assumptions on the market gain, you cannot do much better than that. This is provable. And in the other case, in the opposite case, in which instead you assume that the market gains are AD from some unknown distribution, the maximizing the expected log wealth is minimax optimally in the short and in the long period. Okay, so if everything is stochastic, the constant rebalance portfolio is the optimal strategy. Okay. And by the way, this is a basic version, but you can extend it to transaction cost. You can use side information. You can use the knowledge of the fact that the market might change over time, so that you want to compete not with a single constant rebalance portfolio, but with a constant rebalance portfolio that is changing slowly over time. All of these can be done.
So just to ask you, what changes a little bit when you have transaction cost, for example?
Oh, what you have transaction cost, basically, you want to make the algorithm a little bit more, you want to put inertia in the algorithm. So basically, you don't, if the change between your allocation of money between one day and the other is not too big, you want to say to the algorithm, do not do anything. Basically that, yes. And it's not difficult. People have done it, and the regret will not change. Of course, then you will have another term that will take into account the transaction cost.
Can I also ask? So I was thinking that the optimal solution might be simply minimizing over. So to get the optimal you minimize over the whole period. If you minimize over just or given only historical data, do you not get the same solution?
No. So you mean the solution here is the same as the solution, for example, here mid-time?
No, what I mean is that to get the x of t, you just minimize the total regret up to, knowing only the regret up to time small t.
Yes. Yeah. So yes, in the sense that the algorithm calculates this quantity using all the information between at the beginning of the game and.
But with a minimization step rather than it seems to be an expectation. This is what I'm just trying to.
You want to say instead of calculating this expectation, you want to say, let me calculate the best till now and let me use it.
Yeah.
Oh yeah. This is a classic approach in online learning. It's called follow the leader. In online learning, we have a bunch of algorithms. The approach that you just described, it's called follow the leader in online learning.
Right.
And it's possible to show that follow the leader works only if the losses are nice, in the sense that they are strongly convex. If the losses are not strongly convex, if the losses are just Lipschitz, it's possible to show that follow the leader will give you regret that it's linear in time instead of being sublinear in time. Now, one might wonder, are these losses strongly convex? And no, unfortunately, these losses are not strongly convex. And so it's not enough. So follow the leader.
And so this kind of relationships, and when you say linear in time, sublinear in time, it seems like it's independent of WT, because WT is supposedly, you don't know it. It's given by the
adversary.
Stokes.
Yes.
But your results, I didn't see that there's any assumption on WT or
That's true. That's true. The assumption holds for any WT.
So even if WT is crazy,
even if WT is crazy, this is the beauty of this thing. The results that I show you, this is exact. This holds for any WT chosen adversarially, and these are the exact constant. There is no assumption whatsoever.
Right. And maybe for one final question,
yes.
But you said that the prior has to somehow be concentrated around you, around the
prior is this actually. The optimal prior.
I think it's somewhere else.
Okay. The optimal prior is this Dirichlet distribution over your stocks. There is another prior that you might use that is a very simple one. You might use just a uniform prior. And it's possible to show that it's actually worse than this.
So this one, is it concentrated around halves, around our half allocation across board?
No, this is over the simplex. This is
What I meant to say is that you want the prior to be has enough mass around optimal U so that you can
yes,
trade around that.
yes.
Um,
You don't know clearly the optimal U.
It doesn't have to be the mode.
No.
No.
So, quick question. You talk about this not being strongly convex, right? I mean,
I said if the losses are strongly convex, the strategy that he suggested would work.
and is it possible? I mean, in case that are convex but not strongly convex, to add some regularization term that will essentially make it strongly convex?
Yes, exactly that. We call that approach follow the regularized leader. So, sorry, we are not very, we don't have much fantasy. But yes, that is exactly the approach. You have the regularization, and then you can show that, and then you have to tune the regularization, otherwise it won't work. And you can show that the regret will be square root of t. That, by the way, it's larger than this. This is logarithmic. This is sort of apart from constant regret, there is nothing better than this. Okay, everything is good? Yes?
I throw to you. Thank you. A very naive question. Why do you even need the U? It's basically a maximization problem, right?
You don't need U. You don't need U. So this says this regret will be less than log blah, blah, blah for any sequence of W and for any U. So this, given that it holds for any U, it holds also for the best, but you don't need to know U.
Okay, great. Thank you. Yeah.
Okay, so now let me actually show you the interesting part of the talk. This was all known stuff in a certain sense, and for online learning people, this is very, very known stuff. But let me show you what I can do with this algorithm that is a very sort of weird application of it. Okay, now let me show you a problem from statistics, very, very simple problem from statistics. You have a stream of random variables in 0, 1. Okay, so they're bounded. Let's say that there are IID, but well, actually I need something a little bit weaker. The only thing that I need is that the expectation of each one of them conditioned on the past is a certain mu. Okay, that is fixed. And I want to estimate mu, and I want to give confidence interval that holds uniformly over time. This is a classic problem if you want. And so in formulas, basically, I want to generate a sequence of interval ATBT such that the probability that mu belongs to this ATBT for all the time steps is at least some 1 minus delta, and I decide delta. Okay. Now, of course, the problem is trivial if I don't say anything else, because given that everything is in 0, 1, I might just output 0, 1, 0, 1, 0, 1 all the time, and this is true. Clearly, the probability is true. So I want something else. I want the width of the confidence interval to go to 0. And I know that they should go to 0 at roughly 1 over square root of t. Okay, this is roughly the right rate. So how can I solve this problem? I can just use a concentration inequality. So I take the empirical mean of my random variables, and I use a concentration inequality. And I can also use a union bound because I told you that I want them to be uniform over time. So I use a union bound, and this is what I get. I get that after small t iteration, the probability, the unknown mean will be in this interval where this is my empirical estimate, and this is the confidence that I get from my concentration inequality. Okay, where kappa here will depend on the variance of the random variable, and there is log of t over delta and divided by square root of t. And everything is sort of standard here. There is nothing really new. For example, if you use Maurer and Pontil, this is an approach that will give you a concentration inequalities that depends on the empirical variance. So you don't have to assume that you know the variance. Kappa here will depend on the empirical variance. You get exactly this bound. And by the way, everything is optimal here. We can debate if log t is the right thing. It should be log t instead of log t, but everything is optimal. So why am I even describing this problem? The fact is that when you actually use these things in the real world, you will see that they are terrible if the number of symbols that you have is small. Terrible in the sense that you might get an estimate that says your unknown mean is something like 0.8 plus or minus 3.7. And why this is useless? Because I told you, well, all the random variables are between 0 and 1, and you gave me a completely vacuous estimate. And there is nothing that you can do about it. This is intrinsic on the fact that you're using a very simplified expression of the confidence interval. It's also weird, by the way, that your confidence interval is symmetric. Why should it be symmetric? Let's say that you're estimated at Bernoulli, this thing is symmetric. It's clearly wrong. Okay, this is good asymptotically. Asymptotically is optimal, but in the final sample regime, this is terrible. So ideally, instead, you would like something that is non-vacuous, even with one sample. I give you one sample, you should give me a confidence interval that is strictly less than 1 in width. And this is possible. This is completely possible. In fact, I'll show you how to do it. Okay, what is my approach? I will use a portfolio algorithm to derive a concentration inequality. And this is easy. This is so easy that I'll show you in a couple of slides how to prove it. So as a warm-up, let's show a very simple concentration inequality. Let's say that x1, x2, xt are a sequence of ID random variables in -1 and 1. 0 mean. Okay, so here the mean is known. And I want to show that with probability at least 1 minus delta, I have that the maximum over time of the absolute value of the average is less than roughly 1 over square root of t. Okay. And again, this is known. There is nothing new. This is actually even slightly suboptimal. How do we show this thing from portfolio? So the key ingredient is the following: Will inequality. Will inequality says that if you have a non-negative super martingale and the expectation of the first one is equal to 1, the probability of that the maximum of the super martingale is big is actually small. Okay. What is the interpretation of this thing? When Will wrote this theorem, he was thinking to a specific thing. He was thinking about betting. He wasn't thinking about gambling, how to make money. Will is the guy that I discovered while writing this paper, invented the concept of martingales. It's by him. And his entire PhD thesis, it's about gambling. He wanted to use the concept of gambling to define what is randomness. And so when he wrote this lemma, he was really thinking about money. And so what is a classic example of a super martingale? A classic example is the wealth that you make betting money 1-to-1 on a fair coin. For example, you play the roulette and you just bet black and red. The money that you make, it doesn't matter what is the strategy that you have, it's always a super martingale. Okay, and so Will basically saying the probability that the max of your wealth is big and it's small. So it basically says it doesn't matter when you stop, because people say I have a very good betting strategy. I know where to stop. I stop at the moment that I gain a lot of money, and this is the optimal thing. Will says it doesn't matter. It doesn't matter when you stop. Even at the top of your wealth, the probability that this stop will be high is small. Okay. Now we will use this thing. We just need this lemma, and we just need the regrets that I showed you before, and we will prove the concentration. How we do that? First, we have to construct market gains out of this random variable. The random variable that we had, let me remind you, the random variable that we had is in -1, 1, and the mean is 0. Okay, so let me construct 2 market gains. We just have 2 stocks. One stock is 1 minus the random variable. The other stock is 1 plus the random variable. Okay? Given that the random variable is between -1 and 1, the market gains are between 0 and 2. That is completely fine. These are legal market gains. And it's possible to show very easily that it doesn't matter what is the portfolio algorithm that you use. The amount of money that you will make is a martingale. Okay, this is very, very similar to betting on black and white, but it's in a continuous sense, if you want. Instead of being just +1 and -1, you have everything in between. But given that the expectation of this random variable is 0, the amount of money that you make is a martingale, always. It doesn't matter which betting strategy you use. It doesn't matter which portfolio algorithm you use. And so we can use Wheeler inequality that says immediately the probability that the maximum over time of the wealth of your algorithm is big is small. Okay, this is just Wheeler inequality immediately. Now, this holds for any portfolio algorithm you might use, any in the world. Let's choose a particular one. The particular one that I want to use, it's universal portfolio that I showed you before. Okay? So universal portfolio says the guarantee that I showed you before, the one with the logarithm, and you just have two stocks. If you just take the exp of everything, you will get that the wealth of the algorithm is at least the wealth of the best constant rebalanced portfolio divided by square root of t. Okay, this is the regret. This is exp of the regret. It's exactly this quantity. And so we can, and this is true for without any assumption on the coin. Remember, this was true without any assumption on the market gains. So this is true without any assumption whatsoever. And so we can go back here and we can say, what is the wealth of my algorithm? The wealth of my algorithm, given that I am using universal portfolio, is I can lower bound this probability with the same thing in which here I put the wealth of the best divided by square root of t. Because again, this is, my algorithm will make at least this amount of money. Might make more, but at least this is true. Okay. Now, how much is the wealth of the best for this particular problem? I can calculate it. It's very boring, but trust me on that the wealth of the best on this particular problem that I show you is this quantity, exp of the sum of the random variable squared divided by t. Okay, so I go back here, and again, I lower bound it with this quantity. And so I have that exp quantity divided by 1 over square root of t. It's finished. The theorem is finished. I just have to invert this inequality. I just have to say, okay, this is the probability of failure with probability at least 1 minus delta. The opposite will happen. I take this quantity inside here. I solve for the sum of the x, and I get my theorem. Okay. So this might seem like a magic trick, but let me tell you what is the idea behind this. We basically prove that the existence of an online investing algorithm that guarantees you a regret implies the existence, immediately implies the concentration inequalities. Okay, and this is not true just with the universal portfolio. This is true for any algorithm that you like to do betting. If you can show that your algorithm is good in the sense that it guarantees a regret, immediately this implies a concentration. Okay, so there is it's a link only in one sense, but it's also possible to show it in the other sense. We will not do it. Okay, so is it clear? Was it clear what was the basic idea at least? Okay, now again, I told you this is not an interesting concentration in any sense because it's known suboptimal, so there's nothing very interesting going on. But we can do better. So first of all, here I had said the random variables they have zero mean. This is not what we are interested in. We don't know the expectation of the random variable. So we want to put ourselves in the case in which the mean is unknown. So first thing that we do is that when the moment that we construct our market gains, we say it's 1 minus the random variable minus mu. Okay, again, this is a legal market gain because the random variable here is between 0 and 1. The random variable between minus its mean is between -1 and 1. 1 minus this quantity is between 0 and 2. So this is a market gain. It's good. What is the weird thing about this? It might seem that in order to run the algorithm now, I need to know mu. And this is weird because I told you I don't know mu. But the caveat is that I don't need to run the algorithm. I don't. There was never a moment in which I actually, in this proof, I was actually running the algorithm, right? I just have to know that the algorithm exists. If the algorithm exists, it doesn't matter if I can run it or not, it will guarantee me a concentration. Okay, and so this is the trick that allows me to put here the mu, even if I don't know it, because I don't have to run the algorithm. The other thing is that we don't have to do the step in which we lower the optimal wealth in order to get a nice formula. Let's say that we don't care about nice formulas. So, you know, lowering the wealth will give you something manageable, but it for sure will give you a worse concentration. So let's not do that. And the other thing is that the regret guarantee can be improved. It's possible to show that the universal portfolio gives you a regret guarantee that it's a little bit better, just a little bit. But again, anything that gives you a better wealth will give you a better concentration. And also, we can use a more refined reduction. Instead of using this one that is simple, there is a more refined one that uses explicitly the fact that these random variables are not between -1 and 1, but are between minus mu and 1 minus mu. And so you can do something a little bit more refined. But I know I won't go into details. So if you put all these tricks together, now this is the actual algorithm that you can show. That basically says that the probability of the maximum of this ugly expression being large is small. What is this ugly expression now? This is exactly the same thing that we did before. This is again a wealth minus a regret. Same thing. But the difference is that I don't want to simplify the ugly expression. I leave the ugly expression as it is. And then I solve numerically. Okay? Before, I lower bounded the wealth with the exponential quantity because I wanted to solve for it. And I wanted to show that the concentration has a familiar phase. But let's say that I don't care about the formula. I just want to calculate the confidence interval. I should not lower bound it. And so this is what we do. This is now our implicit concentration, if you want. And the only thing that we have to do is that we have to solve numerically for the set of all the mu that makes this the opposite of this thing true. And we will get the concentration. Okay. Again, before I solved symbolically, and now we just do it numerically. Now, it might seem that this is an hard problem because it might seem that this might be maybe a non-convex problem, very difficult to find. But it turns out that we can show that the set of all the mu that satisfy the opposite of this inequality is an interval. So you just have to find one extreme and the other, and you can just use binary search. Binary search for one extreme, binary search for the other extreme, and that's it. And so the final algorithm is this one. It's very ugly, I know, but I just want to show you to say that it's not insane. This is implementable, and in fact, I mean the code is on my website. And we call it precise portfolio regret for confidence sequence based on the algorithm of cover. And so what we can show, I cannot show you a very nice formula because again, I avoided doing simplification because the simplification would give me a loose formula. But I can tell you that asymptotically, this is the intervals that you get have this shape, where this is the empirical variance. And this is, again, the right one up to the logarithmic term that should be log-log. But there is an even more important property. We can show that this is always non-vacuous. Even with one simple, the confidence interval that you will get are always non-vacuous. Now, let me deal with the fact that the optimal dependency should be log-log t instead of log t. This is also possible. You only have to change a little bit the prior that you use in your universal portfolio. Instead of using the Dirichlet 1/2, 1/2, 1/2, you have to use a prior that is basically the same one that Robbins used when we showed the law of iterated logarithm. And you can get now this other confidence interval asymptotically that has the optimal dependency on time. It's log-log variance instead of being log t. Okay. A few words on this idea. All this might seem really weird, but actually, in the latest years, there are a lot of people working on this. Sometimes they call e-values. Peter Grubwald is doing a lot of work on this field. But we started from a completely different view. We started from this paper in which they showed that online learning and martingale-tail inequalities are equivalent. This was a seminal paper for us in online learning. And the equivalence goes both ways. So this means that any online learning algorithm will give you a concentration, but any concentration will give you an online learning algorithm. There is a very famous paper that recently has been also used in empirical work, that is Bowdy, Smith, and Ramdas, in which they use a similar ideas, in which they used betting algorithm to create concentration inequality. The difference is that they used betting algorithm without any guarantee. Because the approach works for any betting algorithm. Wheel inequality does not say you should have a guarantee. It just says, give me a betting algorithm, whatever. It's always true wheel. And so they used heuristics betting algorithm, and they showed that empirically, things work very well. And asymptotically, again, things are good, but they cannot show anything finite time. But the idea comes from before. There is a paper by Hendricks that is only on arXiv, in which as far as I know, this is the first time that this approach was implemented for real and shown to work. But there are also two books. I mean, Hendricks was based on his idea directly on the book of Schaefer and Bovk, in which Schaefer and Bovk had a much broader aim. They wanted to completely remove measure theory from probability and use instead gambling instead of measure theory in order to construct the entire theory of probability. But you can go even farther back in time, and you will discover that Kober in '74 has rejected the annals of statistics, in which he casts testing as a betting game. And everything is in that paper, the optimal betting strategy, even connection to Kolmogorov complexity. It's a very fascinating paper. Okay, so last few minutes, let me show that this actually works. I tried 4 different sequences of IID random variables, Bernoulli, 2 Bernoulli and 2 betas. The probability of failure is 0.05. I compare with the Vacuous, Smith, and Ramdas, and I compare with Howard et al. That is the state of the art with if you care about formulas. If you don't want to solve things numerically, if you just want the best formula ever, this is the paper that you should use. My code is online, by the way. And these are the results. So this is a Bernoulli 01. This is number of simples, and this is the confidence sets that you get. So it's upper and lower bound of your confidence set. This is a Bernoulli 01. So you would like basically these two, the confidence sets to shrink to the true mean, that is 01. And all the methods are doing that. However, you can see that the state of the art with formulas up to, what is this, 30 simples give you a vacuous interval. So up to 30 simples, completely useless. There is 0 information out of that concentration. The approach of Vacuous, Smith, and Ramdas, it's much better than the formulas, but the same up to a certain point, completely vacuous. This is our approach, and I don't know if you can see it, even with 1 simple, this is 1 simple, this is a logarithmic scale, but this is 1. 1 simple, it will give you a confidence width that is strictly less than 1. And it might seem that, asymptotically, they're all the same, but if you plot things on a log-log plot, you will see that my algorithm, that is the red one, and the violet, that is the state of the art with the formula, they are correct. But the approach of Vacuous, Smith, that is based on these heuristics, asymptotically will be completely off in the way in which it decays to 0. And by the way, this is not unexpected. If you look at how they do things, this is completely expected. And same story goes on in the other cases. This is a Bernoulli 05, this is a beta 11, and it's always the same. Our approach dominates all the others in the small sample regime. Asymptotically, it matches the performance of the best formulas. It beats the heuristic approach. And I want to also underline the fact that, for example, this is a random variable where the variance is kind of big. And so you can see that here we are at 10 to the minus 2 as the confidence width. This is instead a random variable in which the variance is much smaller. And you can see that this thing is converging to 0 much faster, because this is exactly what you would like to have. The algorithm has to adapt to the variance. Okay, that's it. So if you want to forget everything, this is basically a summary of the talk. Universal portfolio, you just use Wheeler inequality, you get a uniform time concentration. Okay, thanks.
Any questions?
Well, thank you for the great talk. So all your results are for random variables in 0, 1.
Yes.
So I guess if it on a bounded interval, you can rescale, but you need to know the bound.
Yes.
And if it is unbounded, can you do
Right. So if it is unbounded, you can still we have a paper in which we did that, but I cannot claim that it works so well as this one. Because the moment that things are unbounded, okay, what is the practical problem? Suppose that you're playing the roulette and you bet money. What does it mean in our reduction that things are unbounded? It means that you bet money and you don't know how much money you will lose when you lose. You might lose more money than what you bet, because the multiplier is unbounded. And so this means that you might place a bet, you might lose all your money, and that's it, game over. You cannot play the game anymore. And so things are annoying. You have to do things. You have to assume stuff. You have to do all sorts of approximation, and they do not work so well as the bounded case anymore. So you can do it, but it's not good.
In the bounded case, if you are away from 0, 1, so you need to know the bound.
Yes.
How robust is estimate with respect to the bound?
Oh, I never actually tested it. It's a very good question. You might. I mean, you need an upper bound that is correct, right? Otherwise, the algorithm will not work. But your upper bound might be loose. So this is the case. I don't know. It might be. Oh, okay, I think the final bound will depend on the variance anyway. Asymptotically, you will not depend on your upper bound. You will depend on the variance. So it might be robust, but I should double check.
Questions?
Yeah, thank you for the very nice talk. I have a big question that comes from a rather naive thought, I would say. I'm considering the situation when you have a market competitor that decides to try to fool you in the sense that he's buying, for example, buying stocks in a way that is suboptimal for him, but might lead you into a wrong strategy. Because then I think in this setting, the streamed input data would be non-martingale anymore. Now, just wanted to ask if you see any way of maybe generalizing it to such a setting where you have like aggressive competitors that try to fool you.
Okay, so one thing. The competitor never plays any role in anywhere. Okay, so you compare your performance with respect to this guy, right? But you never observe this guy in any way. It's never in the real life. This is sort of an ideal thing where you tend to that thing, but you never observe it. Okay. The other thing that you ask is if things are not a martingale anymore. The portfolio still works. Portfolio doesn't depend on anything. Portfolio is adversarial, but Will inequality depends on this. So if you are aware of any way to extend Will inequality to the case that things are not exactly a super martingale anymore, it might be that this approach might go through. I don't know, because my expertise in the end it's online learning. It's not really statistics. So I hope this answers your question.
Thank you.
I have one. So at some point you said that if you change the prior, you can improve the results. I didn't quite get where you use the prior, because I thought you don't use the wealth bounds anymore for your results.
Right. What is the role of the prior? The role of the prior is here. The regret will depend on the prior. It's the only place where the prior plays a role.
Mm-hmm.
So this log t here is exactly the reason why when even in the warm-up thing we got log t here.
Yeah, but at some point you said that you're not using the wealth bounds anymore.
The regret is still here. You see, this is my regret.
Right.
So whatever regret you have, it will appear everywhere, and it will give you the concentration until the end. Even here, this is the regret.
Okay, so if you go back to the previous two slides,
I don't know if you're mentioning this part in which I said we can improve.
Yeah, that's the one.
Yes.
It's just if you go back to the previous two slides, when the warm-up example, the proof.
Yes.
So you use the first line, but you don't do the second line, the bound. Is that right?
I do the first line, but I don't do the second one. Exactly that. Yes, but I still use the regret. So unfortunately, the regret is there. Yeah. You could. By the way, there is another paper that built on our paper in which they say, you know what? Let's actually run a universal portfolio. Let's not even do this inequality. We can just run directly universal portfolio, and this is strictly better than taking the regret. The regret is worst case, right?
Yeah.
And they find a way to do it through dynamic programming. The annoying thing is just run the algorithm.
Right.
I wanted something easier. In my case, it's much easier to implement. I mean, the algorithm, this thing, it's easy in the end. I mean, I think their approach is much more difficult to do it, but it's slightly better.
Right? Any more questions? Not, let's break for lunch and thank the speaker. The lunch is until 1:30, I think. Yeah.